In this video, I'll introduce you to some of the most important rules for circuits, but before doing so, I wanted to make sure we talked about exactly what a circuit is. So a circuit is defined as a closed conductive loop, and for it to be a useful circuit, it has to have a voltage source and something called load. So a voltage source can be something like a battery. It could also be something that, like when we plug something into a wall, that we could think of that wall outlet as the voltage source. And then a load is something that'll take that electrical energy that's given to the electrons and convert it to some other form. So I have a diagram here that shows a closed circuit on the left-hand side. In this case, my voltage source is a battery and my load is a light bulb. So that's taking that electrical energy and converting it into thermal energy, which we know creates light. If we have an open circuit, then you'll notice that there is no complete path for electrons to flow, and therefore nothing really happens. Also note in this diagram, those yellow arrows that we see are coming out of the positive end of the battery because, as we've previously learned, current flows from the positive to the negative, just as positive charge would flow from the positive to the negative around the circuit. If as I already mentioned, if we don't have a voltage source, then we don't have any current because we don't have an electric field causing the electrons to move. And if we don't have a load, or perhaps if the load is too small, so it's unable to convert all of the electrical energy into some other form, then we have what is called a short circuit. If that happens, then our electrons will start moving faster and faster and faster, and when things move really fast, we know we get a lot of heat, and so often short circuits can result in a fire. Or just a really hazardous condition, fire, or we could melt things. Obviously, that's not something that we want to have, so we want to avoid short circuits at all costs. Now, we mentioned that all circuits need a voltage source, and so in AP Physics, sometimes we'll call that voltage source an EMF. Again, basically, we need something that is doing work on the electrons to keep a potential difference between two terminals. So the two ends of the batteries can be called terminals, the positive and negative end, or the two prongs of a plug would be our terminals in this case. So we have the EMF device that is supplying that energy that's necessary for the electrons to travel through the circuit. That term EMF is actually a really outdated name for this. It actually used to be called electromotive force, and that's where the EMF comes from, kind of an abbreviation of electromotive force. And that term came about before physicists understood exactly what was happening in the circuit, before they really understand the idea about electrons flowing. But that term, even though we no longer call it an electromotive force, we've kind of kept that idea of EMF as being the device that kind of creates that electric field in order to do work on the charges. Inside the EMF device, so again, when you see that word EMF device, you can kind of think of battery. That's probably our most common one that we'll use. Electrons are moving from a higher potential to a lower potential. So they're moving from the positive to the negative side. And that's different than in circuits, because in circuits, as you saw on that previous slide, they move around the circuit from the electrons are coming out the negative and going to the positive. Lastly, in AP Physics, you'll see things about an ideal EMF device or a real one, like a real world. So an ideal EMF device, so like an ideal battery, has no internal resistance. But in the real world, our devices do have internal resistance. And so when we have a real battery or real EMF device, we will often draw it as that battery symbol and a resistor symbol, and we'll kind of treat it as if there's just another resistor in the circuit. Now, I mentioned at the start of this video that we're going to learn some really important laws. So now that we know exactly what a circuit is and we understand that idea of the voltage source or the EMF device that we need, we're going to learn about two laws that are crucially important to the study of circuits. And they're called Kirchhoff's laws. You'll notice the spelling of Kirchhoff is a little bit different, probably not what you would expect. I promise it's not a typo. He does have two H's and two F's in his name. These two laws are really fundamental, and you can use them to analyze any type of circuit, no matter what's in your circuit. We call them Kirchhoff's laws, but their names are rules. I'm not quite sure where that comes from. The first one, though, is called the junction rule. And that junction rule says that the total current entering any junction must equal the total current leaving that junction. And really, this is a consequence of conservation of charge. So to understand exactly what that means, we kind of need to know what a junction is. So if I have a circuit where there is a wire and then there might be a split up, so I might have something like this, and perhaps I have some resistors. We'll have something that looks like that. Let's say this right here would be a junction. Junction is defined as a place where two wires come together. So if my current were traveling along this wire in this direction, then some of the current would go this way and some of the current would go that way. And this current here, if I call this I1, let's say I call that I2 and that one I3. So that current I1 would have to equal to I2 plus I3. I1 is the only one coming into the junction. I2 and I3 are the ones leaving the junction. The other of Kirchhoff's laws is called the loop rule. And the loop rule says that the sum of the potential differences around a closed loop must equal 0. And this happens to be a consequence of conservation of energy. So basically what that's saying is whatever energy you gain has to then be lost as it travels through the circuit. And if you think back to Unit 1, we know that potential difference is just the energy divided by the charge. And so that's why we're allowed to use potential differences here. So when we apply the loop rule, we will often be looking at positive or negative potential differences. And whether a potential difference is positive or negative will depend on whether we are going from a positive to negative end of our device or if we're going from a negative to positive end of our device. So much like we do with lots of quantities in physics, we'll always think of final minus initial. So if we're going from a positive to negative end, we're doing a negative minus a positive, we'll end up getting a negative potential difference. Or if we go from negative to positive, we'll end up with a positive potential difference. We will, of course, use these laws a lot. So you'll see several examples of applying these rules. We have one more thing to talk about in this video,